take it or leave it, it's up to you. So I'll do one with trig. And I'll leave one for you to try. So find and investigate the critical points. Right, so this is what I was alluding to before, where I was saying sometimes your partials will be in terms of both x and y. All right, so f sub x, hang on to the sign of y as a coefficient, and then take the derivative of the cosine of x, which would be negative sine of x. Then f sub y, hang on to the, because the coefficient really is cosine of x, so hang on to that, take the derivative of sine of y, which is cosine of y. All right. So these need to be equal to 0 and also equal to each other. So negative sine x sine y equals 0, and cosine x cosine y equals 0. All right. So this is an and situation. Normally I don't bother with the notation when it comes to solving quadratic style situations, I overuse that word, equations. But here it's very important because the solutions for this have to coincide with the solutions for that. All right. So within each equation, I'm solving for x and y. So I'd write it as the sine of x equals 0, or the sine of y equals 0. Because if either of those are 0, then that first equation zeroes out. Cosine of x equals 0, or cosine of y equals 0. All right, so you've been studying your unit circle. Where is the sine function equal to 0? 0. 180. And so on, right? So 360, and, it maybe go negative 180, dot, dot, dot. All right. Same thing would be true for the y. So, or y would be equal to 0, 180, etc. And, all right, so where's cosine equal to 0? 90, 270, etc. Same thing for the y's. Or all right. Now you look at the diagram, and that's why I was saying that I'll give you the diagram, because in the last question you knew to be on the lookout for one answer. We got our one answer. I was satisfied with that. We moved on. Here, I mean, I see lots of hills and valleys. All right. So that means that there's going to be a lot. Right. And so infinitely many, in fact. What we want to do is come up with a rule or set of rules that would define our max and mins. All right. So what I need is any possible pairing of x and y that would make both of these equations equal to 0. All right. So that's the hard part, because that requires the most thought. So x and y. All right, so what you could do is pick out just values of x and y that could make sense. Like, for example, 0, 0. Well, 0, 0 is not going to work, because while it makes this one equal to 0, this one would be equal to 1, because cosine of 0 is equal to 1. So 0, 0 is not an ordered pair, even though I have a 0 here and a 0 there. It doesn't work for both equations, so that's no good, all right? But if I take a 0 for x, and really anything but these values for y, I'll be in good shape, all right? Because if I take the 0 for x, that's going to zero out my first equation, all right? But it won't zero out my second equation. So then I look to my y's here, the y's that would make this one zero out, because it doesn't matter what y is here, because the fact that x is equal to 0 already zeroes out this whole shebang. All right, so if y is equal to 90, then this is going to be fine, because that's going to make the cosine of y equal to 0, which zeroes out the entire right-hand equation. So 0 and 90 is a possible ordered pair. We could also say 0 to 70. All right, so basically we're at a rule here. It's 0, comma, 90 plus 180k. And we'll define k as belonging to the set of integers, but we'll do that all in one shot because this isn't our only possibility, all right? So then another possible case would be, okay, well, what if I did the same stuff, but I used a 180 for x? Well, true. So I could say 180, because 180 is going to zero out my first equation, but it won't zero out my second equation if I pair that with a 90, a 270, and so on. All right, so then I would be saying, instead of 0, comma 90 plus 180k, I'd be saying 180, comma 90 plus 180k. All right, but if I follow that progression, well, the next one in the list would be 360, and then 540. You know, so would it be 540? Yeah. So then we could generalize that even further by saying, all right, well, these seem to be giving me the set of 180 plus 180k. I'm sorry, 0 plus 180k. I mean, I guess 180 plus 180k would have worked too, but. All right, so instead of writing out every possibility, we came up with a generalization. And then we'll figure out, using our second derivative test, whether this generalization gives us a max or a min. And the good news is, I don't have to use the k's. I just have to use one of my points, all right? And that'll get the job done for me, all right? Because what applies for one of them will apply for all of them. All right, another case, all right, because I focused on the x values here, but I have a set of y values that would make my sine function equal to 0, all right? But those y values won't make the cosine equation equal to 0, all right? Because that would make it either 1 or -1. So then if I pair these y values with these x values, for example, if I did 90, along with 180 degrees, that would get the job done, right? Because 90 for x would give me something for the x that's not equal to 0, but when I plug in a 180 for the y, that'll zero out, all right? 90 for x, that zeroes out, so I don't even care about what y is there, all right? But basically what we're going to get at is the reverse, all right? So the roles will be swapped. So another possibility would be, instead of saying 0 plus 180k, we could say 90 plus 180k and then 0 plus 180k. All right, so now I'll define what k is, where k belongs to the set of integers. All right, so you think back to the last problem, all we did was we took our partials, set them equal to 0, and solved. We got a 1 and a 3. We were done with that in like half of a heartbeat. Here, it took like half an hour, you know, so 10 minutes, I got to counter. But I mean, it's definitely a lengthier process. And we haven't even taken the second derivative yet. We have to do that. My second order partial with respect to, well, it depends on what I'm starting with. So I need second order partials with respect to x, y, and then if I want the mix, I can go x, y, or y, x, because sine and cosine functions are everywhere continuous, so I'm not worried about there being a discrepancy there. All right, so f sub x, x. So hang on to the sine of y. Take the derivative of negative sine x, which is negative cosine of x. All right, f sub y, y. So we're looking at hanging on to the cosine of x, taking the derivative of cosine, which is negative sine of y. So as it turns out, the second order partials are going to be the same. All right, it doesn't always happen, but sometimes it does. Now my second order mixed partial, f sub x, y, is fine. I mean, either way would work. All right, so I'm going to hang on to the negative sine of x and take the derivative of cosine sine of y, which is cosine of y. So I get negative sine x times cosine of y. So the discriminant, d, I could start plugging numbers in, but it's going to get pretty hairy pretty quick. So it's kind of, I don't want to say it's in our best interest, but you know, it seems like maybe doing it in general terms first would be the way to go. All right, so it kind of cleans up nicely. Well, kind of nicely. So, because this is the same as saying negative sine y cosine x. And this is the same thing. So, the first part of the discriminant is just multiplying my, my two partials, f sub xx and yy. So, sine squared cosine squared. Sine squared y cosine squared x. Minus, now I want the mixed second order partial squared. All right, so minus sine squared cosine squared, right? Sine, but in terms of x and y. All right, so the almost heart attack can subside and you can start to relax, because if the x and y were swapped, this would zero out and it would be inconclusive, which would mean that you would have to use a completely different technique, which would suck because you did all this work, right? So we dodged one there, all right? So what I want to do now is find, because I have two cases really. I want to find my discriminant for the two possible cases. So I'm going to use the 090 because I know that's a good representative of my first scenario. All right, so 090. So I'll find the discriminant at 090. All right, now it is possible it could still zero out, which would be pretty awful also. Rut. squared it, right? Oh, okay. Yeah, I'm still having heart attacks here. Right, I thought it was all going to zero out, but I was mentally swapping things in my mind because you see the zero first, and you see the sign first. You're like, that's going to zero out, but it's not because we're putting the 90 in here. So this is going to be a 1. That's going to be a 1. And then this part, we're putting the 0 in for x. That part is going to zero out. So the discriminant at this location is just going to be a 1. Then I do it again, but for 90, 180, for example. I mean, you could do it 90, you could do 90, 0 if you want, but it's all the same. All right, so if I plug in a 180 for y, that's going to zero out. But if I plug it in for x here, it's going to become, I'm sorry, I plug in the 90 for x here, it's going to become a 1. Plug in the 180 for y, it's going to become a negative 1 squared, which is a positive 1. So this whole thing becomes a negative 1. That's the long and short of it. But all those pregnant pauses there were for the purpose of me not screwing this up just by accidentally transposing what goes in for x and what goes in for y. All right, so we have discriminant values. All right. I also need to know what the sign is for my second order partial with respect to x. All right, and I got to do that for these points also. So I'll just kind of jot that off on the side here.
How are we having the quiz?
Like the last 10 minutes. Yeah. All right, so we're popping these values into my second order partial with respect to x. All right, so plugging in a 90 for y is going to give me a negative 1. I'm sorry, positive 1, ultimately negative 1. Plugging in a 0 for x gives me a positive 1, so this ends up being a negative 1 overall. Plugging in a 90 for y. I just wrote this one, 90, 180 is what I wanted. I wrote the same thing, it's the same equation, or same type of point. So 90, 180. Yeah, better. So plugging in a 180 for sine, that's going to zero out. All right. All right. Yeah, it looks good. So, just off on the side here, I'm going to make little notes here. So 0, 90 was for the first type of coordinate, and for that we know that f sub xx is less than 0, and the discriminant is greater than 0. All right, for the second one, f sub xx is equal to 0, and the discriminant is less than 0. This is saddle point. All right, so local max at these locations all right, but the one thing that we seem to be missing would be local mins. All right, so now what we have to do, I mean, it should have actually come up in this process, but clearly I neglected some sort of pairing of values that would have also given 0. But by process of elimination, we've identified the local max. They're going to occur at these points. Local saddle points will occur at these points. If I could just identify the other pairings of x and y, that would give me 0 for my first order partials, then I'll know where my local mins would have to be. All right, so we want to consider that. So I did X from this one paired with a Y from that one. We did X from this one paired with a Y from that one. What am I missing?
I think it's when you combine them with the k's being the same. Like if you put in k equals 1, you're missing out on a point like 0,270.
Oh.
So I think it's skipping every other point.
Ah.
So you're going to have 4 pairings where 2 of them don't work and the other 2, one's local max, one's local min.
Gotcha. So let me see if I can salvage this. So 090 we did, 0270 is the one that would give me a 0270, if I plug that in here. Yeah, that's the one that would give me positive. Okay. Yeah, it's a relatively easy fix. So f sub xx of 0270 would have given a positive 1, right? And so it's embedded in this whole shebang here. So yeah, there was an overgeneralization, so that's no good. Yeah, so we'll have to break it up into 2 separate categories. So the first, well, actually the first one's fine, right? I just need another one for 270. And so, well, the first one's almost fine. So I'm gonna make this 360K. So that it'll skip over every one of the 270s. And then we'll have another one, 180K, 0 plus 180K. Because that part I think was fine. We just need the 270 plus 360K. All right, so for this one, we have f sub xx. Well, this is what we had before, is less than 0, with the discriminant being greater than 0. And this one had f sub xx greater than 0, with the discriminant also being greater than 0. Right? So we're talking about local max and local min. Right, so, you know, little extra stuff in there makes it a little bit more confusing, but so you look at what we did here, remember that beast, all right? That's something that I would never put on a test because that would just be mean. That's not to say I wouldn't put a trig problem on a test, but I mean, I'm not going to put anything on a test. I mean, this would take the whole test session. So, and also I'd have to read it, right? So just what I was talking about before with the whole simplifying. I don't want to have to grade this either, all right? But this is something that's fine. Also, simpler trig problems would be fine. But that previous question, number 2, it's like a wrench problem. You know, the old dodgeball reference, if you could dodge a wrench, you could dodge a ball. You know, so if you could handle a question like that, then you could probably handle pretty much anything. All right, so first order partial with respect to x would be negative 2x. First order partial with respect to y would be 2y. Set them equal to 0 to find your criticals. 0, and 0. All right, you don't have to worry about that balancing act like in number 2, because my first order partial with respect to x is only in terms of x. So I don't have to worry about what happens to y when x is satisfied. And just like for my first order partial with respect to y, I don't have to worry about what happens to x when y is satisfied. All right. So x is 0 and y is 0, which means that we're looking at a critical value that would be at the ordered pair 0, 0. All right. So now I get into my second order partials. All right. So f sub x, 0. F sub y, also 0. Then the mixed second order partials. Oh wait, sorry. Negative 2 and 2, right? Yeah. I was doing mixed partials the whole time. So negative 2 and 2, yeah. That one's the only one that's going to be 0. All right, so I need my discriminant. Negative 2 times 2 minus 0 squared is going to be a negative 4. All right, so from the picture, I mean, if you look closely enough, it's there. It's just not really the easiest thing to see. So d is less than 0, therefore saddle point at 0, 0, 0. And again, we get that last 0 just by plugging these x and y values into the original function. All right. So this is actually a hyperboloid. So it has characteristics of a hyperbola, except it's in 3 dimensions. So if you kind of look at this, it's sort of like a tunnel. So it has a little hump in the middle, but that hump is neither the highest nor the lowest point on the entire interval, right? So when you get to 0, and that's the problem, you can look at it and say, well, if it turns around right there, that's fine, right? That could be the lowest point. The problem is, so it's kind of weird to think about, it's the lowest point if you look at it from this perspective, but from this perspective, it's the highest point. So it is both the highest and lowest point simultaneously. Since it's neither one nor the other exclusively, it can't be defined as a local max or a local min. Now, if you restrict your domain, maybe you can make a case, but because there's that contradiction, it's really, that's just how it has to be. It's simple. And also, I mean, if I could actually make this look good on paper, you would see that it kind of looks like a saddle, like the kind that you put on a horse, right? Because that's really what it is. You should be able, if it's a saddle point, you should be able to sit on it, all right? Like when you're riding a horse, all right? So that's right there. So here's the horse, there's his face sticking out, and forget about that end. That's you sitting right on, all right? So it has its name for a reason. It's not like some math word that was made up, and it just so happens to be something that is also in the real world. It's actually named after the saddle that one would put on a horse. Right? So, cowboy mathematics. Nah, that was way before cowboys. All right. If I'm not mistaken, I mean, I guess I could rewind some video and find out. Hopefully I teased this one as being the kind of problem that you might consider doing a different way, because it says shortest distance from the point to the plane. You have a formula for that we learned in the last unit, right? But there's also multivariable calculus techniques that we can use to find this distance. So, when all is said and done, at the end of this course, you'll remember some things about vectors. You'll remember some things about vector valued functions. I'll be shocked if you remember the formula for curvature. But I think you'll remember things like partial derivatives and mixed second order partials and stuff like that. Whether or not you call it that, it's like I knew to take the derivative and hold a variable constant. Those are going to be like the hallmarks of the course. All right, so when all is said and done, you're probably not going to remember. I mean, unless you're really good, like memory wise, mine's shot, but you're probably not going to remember the formula for finding the distance from a point to a plane. All right, but you will remember how to take a derivative, and so that's where we're going to go with this. So my plane is defined as x plus 2y plus z equals 4, and we have some point living out here in space. All right, that point has a certain distance away from that plane, and that's what I'm looking to find. All right, that point again is living in space. We know the distance formula. All right, the distance between 2 points in space, depending on what the points are, could be easy to find or maybe not so much. But distance, assuming my pen wants to work, is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. That's if you're in 2 space. In 3 space, we throw the z component in there. All right. Now, what I want to do is minimize this distance. Because if I generalize this by saying, well, it's the distance between this point and this plane, it could very well be that point and this point on the plane over here. Or maybe over here. Or over here. There's infinitely many possibilities. All right. By finding the distance between the plane and the point in general terms, I'm really saying the distance between any point on the plane and that point. All right. Oh, so that's frivolous. So what I want is the shortest distance between that point and the plane. All right. If I find that shortest distance, then I'll know what that distance is, how far that point is away from the point. All right, it'll give me that orthogonal distance. All right, so, well, we know something. One thing that we do know is that there is a finite point that's been established. It's 1, 0, negative 2. All right, so I could chuck that information in there, 1, 0, negative 2. So of x2 minus y2 minus and z2 minus all squared. All right, and it simplifies a little bit, but not in the way I want it to. All right, because I have a function of 3 variables. If I could clean this up a little bit, I'd be a happy camper. All right. One thing that I'm going to do before we actually really kind of get going on this is I'm going to square both sides just to get rid of that radical. I don't need the minus anymore. All right, now I can do that because whether I minimize the distance formula or I minimize the squared distances, they're still going to minimize in lockstep with one another. Right? So if I find the minimum square distance, that would coincide with the minimum distance itself. Right? It's just like saying you have 3 sides of a triangle. 9. I'll keep it even simpler. 3, 4, 5, right? 3, 4 as the two legs and 5 as the hypotenuse, right? By plugging them into the Pythagorean theorem, I get the 9, the 16, and the 25. So as the 5 goes, so does the 25, because they're in lockstep with one another. One is just the squared value of the other. All right. And so that's all we're doing here. We're just saying that let's minimize this because it's going to be easier to do. And once we figure out what minimizes the squared distance, then we'll also know what minimizes the square rooted distance. All right. But I don't want to function with 3 variables if I have any control over the situation. So I go back to this piece of information. I know that x plus 2y plus z is equal to 4. All right, so what I can do, I'm just going to kind of focus on that for a second, is I'm going to solve it for one of the 3 variables. All right, because I want to get it down to a function of 2 variables. One would be ideal, but I don't have enough information to do that. But what I can do is solve for z in terms of x and y. So 4 minus x minus 2y. And x and x and y are free variables. They could be anything. Which actually ties together with what we did in the last unit when we were trying to find the distance between 2 planes. We would find a point on the plane. What we would do is we would arbitrarily select an x and y value and then just figure out what z had to be in order to make it work. All right, so we'd plug in something for x, plug in something for y, and then solve for the z. Same idea here. All right, you have free control over what x is going to be and what y is going to be, but z is dependent on what x and y are. It's kind of like degrees of freedom if you know anything about statistics. And in fact, it's exactly that. All right, so what I'm going to do is I'm going to let x2 be equal to the x value, y2 be equal to the y value, and z2 be equal to the z value, which happens to be 4 minus x minus 2y. So I can chuck all that stuff in there and simplify. All right. Now, it looks like it's going to get out of hand pretty quickly, but these are partial derivatives that we're going to take. So when we find our partials with respect to x and y, we're able to ignore a lot of the other variables. Right? So it actually won't be as bad as it might seem. All right. So I'm going to rewrite. I'll do it over here. Nice one. So for the z's, it's going to be 4 minus x minus 2y. Is it minus 4? Oh, plus 2 squared. All right, so that's the model I'm working off of, and this will give me my squared distance, which in turn will give me my actual distance. One slight adjustment as I'm going through the process of simplifying would be to consider that this is now a function of 2 variables, x and y, so we could write it as f of x comma y. I don't think there's any benefit to distributing out the x. Oh, it was z plus 2. So the best I could do here is combine a couple of terms, the 4 and the 2. So 6 minus x minus 2y squared. All right. So now we get into our second derivatives test. First order partial with respect to x. So little chain rule for the x term, but not crazy chain rule. It's just 2 times x minus 1 times the derivative on the inside, which is just a 1, so irrelevant. Then plus y squared, that differentiates down to 0, plus a little bit more chain rule, but not like crazy chain rule, because again, we're just taking the derivative on the inside with respect to x. So the 6 and the negative 2y are irrelevant. We just have a negative 1. All right, now we are going to have to do something with this, so it does serve a purpose to clean it up a little bit. 2x minus 2 plus 12 minus 2x up, but then I'm going to multiply it by a negative 1, so actually let me highlight that. Let me move and highlight. For some reason that's a thing, I don't know why. All right, so it's the negative 2 that's going through. So we're looking at minus 12 plus 2x and then plus 4y. So it's like, oh wow, great, the 12's canceled. But unfortunately not much of anything else. So we have 4x plus 4y minus 2. So that's my first order partial with respect to x. All right, I could set it equal to 0 and solve, but it's not going to serve a purpose just yet because I have a function of 2 variables. So we'll sit tight on that for a minute because next up is the first order partial with respect to y. The first binomial zaps away, there's no y in it, so 2y, and then really a lot of the same stuff after that. So plus 2 times 6 minus x minus 2y, but this time times negative 2. But we're still going to do the same thing. We're still going to distribute a negative value. So I have that highlighter for some reason. So 2y, but then we're running through with a negative 4. So minus 24 plus 4x and then plus 8y. So not much in terms of housekeeping here. We're looking at, I'll put the 4x first. So 4x plus 10y minus 24. What did I screw up? Hell of a question. Hell of a question. Oh, you know what I did? I know what I did. It was after I caught my mistake, but not soon enough after. Thank you. So minus 14? Because it didn't actually cancel. Now I got that gaping space there. Brutal. So minus 14. All right. So to find my critical values, what I have to do is set each of these derivatives equal to 0. So f sub x, so first order partial with respect to x, set equal to 0. First order partial set equal to 0, but that ultimately means set them equal to each other. Because if they're both equal to 0, then they're both equal to the same amount, the same quantity. So 4x plus 4y minus 14 equals 4x plus 10y minus 24. 4x's cancel. We're looking at 6y equals, we're adding 24 to both sides, 10. So y would be equal to 5/3. All right, so we have a y value for our critical. We just need the x value that goes along with it. So it's just like solving any kind of system of equations. We have two equations with two variables. Either one of them could help us figure out what x is going to be equal to, so I'll work with both of them. And hopefully they'll give me the same number, but you never know, all right? So I have one possibility, and that is 4x plus 4y minus 14 equals 0. Replacing the y with a 5/3. All right, so 4x plus 20/3 minus, I'll write 42/3 just to have the common denominator, equals 0. So that's negative 22/3 added to both sides. So 4x is equal to 22/3, which means x would have to be equal to 22/12, which would be 11/6. All right. I don't know why I've become anti-calculator all of a sudden. Sorry, I'm coming back to this. Let me just get my calculator up. Oh, I see what. All right, I'm learning. Rid of the alpha. Well, actually, as it turns out, I kind of have to sort of do it this way, but I can at least do parts of it. So I get that, math, enter. Negative 22/3 divided by 4. And then add that to the other side, and we have, yeah, so it's 11/6. And then we can verify it. Now, what I would actually prefer to do, instead of spinning my wheels and doing the same thing with the f of y, just to see that it ends up being the same value, what I'll do is I'll just plug that into the y and verify that it gives me the same value. All right. So by plugging in the 11/6 and the 5/3 for x and y respectively, it verifies out as giving me f sub y equal to 0. So we know our critical values are at the shockingly inappropriate fractional values of 5/3 or 11/6 and 5/3, right? Which kind of stinks. We were hoping to not have to do too much work for this problem, but alas, it is what it is. So now all we have to do is find our second order partials, which seems like it would be, oh man, we got to do that. But I'm going to turn off my calculator because we're not going to need it for that, at least for a few seconds. It's not terrible because this is much simpler, all right? So f sub xx, all right, with respect to x, this is going away, that's going away, this is just going to a 4. f sub y. So long story short, we're kind of over the hump. The hard work was getting to this moment, but the second order partial should never be that bad. So 10 f sub xy. All right, we're dealing with continuous functions. So you could do f sub xy or f sub yx. It will give you the same thing. All right, so this is, if I'm doing this with respect to y, this is going away, that's going away, we're just getting a 4. If I do this with respect to x, this is going away, that's just giving me a 4. So either way, we're going to get it. All right, so my discriminant is going to be the two same types of partials. So with respect to x and y multiplied. So 4 times 10 minus the mixed squared. And I mentioned at one point, well, it had to be last class, because I think that's when we first learned about this, that I would talk to you about where this discriminant formula comes from. All right, so we're going to get there, but a little teaser is that there's a reason why we're squaring this, and it really doesn't have anything to do with, you know, anything more than we multiplied the partials that were the same type of partial. Now we're multiplying the mixed second order partials. But since they're going to be the same, it's the same idea as just squaring them. All right, but there's more to the proof than that, but that gives you a little bit of a sense, hopefully. 24? All right, so therefore D is positive, which means that we're going to get an extreme value here. It's just a question of, will it be a minimum or will it be a maximum? It better be a minimum, because the whole point behind this was to minimize the squared distance between 2 points. If what I just found was the maximum distance between 2 points, then I'm not going to be a happy camper, right? Because if I'm looking at the context of the situation, I'm looking at a distance between a point and a plane. If I found the maximum distance, that's going to be like infinity, because it's talking about going from this point to the point on the plane that's furthest away from it, right? Which would be out at infinity. I definitely don't want that, all right? But fortunately, my first order partial with respect to x, f sub xx, is also positive. Therefore, we're dealing with a min. All right, which is great news, like necessary news. All right, now also, my second order partials are constant, which means that these are always going to be the case for this function. All right, if it was in terms of x or y, I'd actually have to substitute my x and y values in. But as it turned out, we just found the x and y values that would allow for the minimum squared distance. All right, so that can now go into my distance formula. All right, now we were just building our way to this relationship over here by coming up with that squared distance. The reality is I could go right back to this distance formula and be perfectly fine. All right, but I am going to need the z value that goes along with it. All right, so z is equal to, well, I covered it up so I can't see it, 4 minus x minus 2y. So 4 minus 11 over 6 minus 2 times 5/3. (10/3, 20/3). Negative 31/3 minus 12/3, negative 43/3. Why? Why do I do that? Why do I do it to myself? Especially since it's about to be nowhere close to what because I subtracted instead of added. I just need a reason sometimes for my stupidity. Yeah, negative 7/6, which is not negative 43/3, if anybody is wondering. All right, so that's the z value. So I can go right back into my squared distance formula and work off of that. Or I could go back into this and start from scratch, plugging in the original coordinate, because now it's the distance between 2 points. All right, so we already did this work, so why not, you know? So negative 7/6 plus 2. Well, one of them was 10/3, 11/6 and 5/3. So I'm just going to crank out these numbers, and that'll give me my d squared. And then I'll just find d, which will be the square root of that. All right, so I'll just pop a rad over this. So 11/6 minus 1 quantity squared plus 5/3 squared plus, I'll write this as 2 minus 7/6. One less symbol to put in. Quantity squared. Take the root of it. I don't expect it to be a math frackable because I just took a square root. I mean, I could have math fracked the value before it and then put that answer under a radical, but this is fine too. So we're talking about 2.04, I'll say 12 units. All right, so yeah, is this an incredibly roundabout approach for finding something that you could easily find using a formula from our vector days? Yeah. Absolutely. Would you do this if you had access to that formula? So, on a test, you would never consider doing this technique unless you were told explicitly to use this technique. And on top of that, you would have to not have any, like, even the slightest idea that there's a shortcut way of doing it. All right. This is like, in case of emergency, break open glass. Right? You have something to fall back upon if you're in a jam, because ultimately you're trying to find a minimum distance. But this goes back to that trig problem we did on the previous page. Look at all this stuff. I mean, the idea that we could just find a couple of magnitudes and a dot product and call it a day and you'll have your answer. I mean, that as opposed to this. So, you know, if you're one of the folks that will be taking the final exam, a little too far away to even think about that just yet. But yeah, you're not, like, that question could be on there, but you're not going to do it this way. You'll do it using the other way. But this is a good type of question to practice with, because you can get the answer using multiple different techniques. Okay. Same idea for this one. You're talking about a maximum volume. You know, you learn techniques back in even pre-calc that'll allow you to find a maximum volume for a box, but what we want to do is use the techniques that we're learning. All right, so it's really up to you down the line which techniques you want to use to come up with a solution, but it's good now to get practice with the current concept. So a rectangular box with no lid is to be constructed from 12 square meters of cardboard. All right, so actually let me start drawing the diagram concurrently with reading it. So 12 square meters of cardboard. I don't know why I made it so big. Whatever, I'll get over it. By cutting square notches out of each of the four corners and folding up the remaining sides. All right, so this is, I always joke and say, in my Algebra 1 class, the first time we do a question that involves cutting the corners out of a box and folding up the sides, that get ready, you're about to do the same exact problem in every math class you ever take for the rest of your life. And I'm right? Like you've done this, like let's cut four corners out of the rectangular piece of whatever, it could be sheet metal or whatever, they change the theme up a little bit, but it's in every class. And maybe you took a geometry class where you actually had a cardboard box and they told you to actually do it, you know? So you learn about three-dimensional figures. But this is essentially what we're talking about, right? So it's made or constructed from 12 square meters of cardboard. So the overall dimensions of the figure are 12. So I'm going to define my variables. I'll call this y, I'll call this x. And we know that xy is equal to 12. We want to define the volume, right? Volume's length times width times height. So when I cut out these four corners, so these four corners here, what I'm going to be left with are dimensions. I want to do red. That represent, 10%. We're going to have to end class early tonight, I think. Nah, I don't want to give people false hope. I'm pretty sure I have a, yeah. They're like, really? We're leaving early? Nah, I can charge it. But while I'm over here, I just know myself enough to know that I'm going to forget my flash drive, so I'm going to pull it out now. All right, so that's that. So those two highlighted sides will represent the two bases, I guess, for the part of the box that's in contact with the floor. So, you know, like the length and the width. And so the height will be the length of one of the sides of the square cutouts. All right. The issue is we've already used x and y to represent the dimensions of the rectangle, but the reality is we didn't really need to, because I could write one, now that I know the area, I could write one in terms of the other. So I could say y is equal to 12 over x, or I could say that x is equal to 12 over y. Which frees up a variable. All right, because now I can just wipe out the y and replace it with a 12 over x, or I could wipe out the x and replace it with a 12 over y. I could leave it either way. All right, so, but I'm gonna leave it as is for now, because what I'm gonna do is I'm gonna define a third variable that I'm gonna call z as the length of each of these boxes. All right, so each one of these sides could be defined in terms of its relationship between x, y, and z. So I would have x minus 2z as one side and y minus 2z as another. All right, so my volume would be x minus 2z times y minus 2z times z itself. Now you could have functions of 3 variables, you could have functions of 30 variables. But ideally, so in an ideal world, we want a function of 1 variable, we'll settle for a function of 2 variables. Right? So I know now that based off of this, I can make either x or y go away and define this as a function of 2 variables. Now, if you have any foresight going into the situation, you know, force a habit, you let your dimensions be x and y. Maybe you don't do that. Maybe you let them be L and W until you settle in on the structure of the whole thing. All right, but as it stands, I'm gonna work with x and z and swap out the y. So x minus 2z, 12 over x minus 2z and z. And I'll redefine this as a function of x, z. Could be x, y, y, z, x, z, depending on how you name things. All right. Now we're looking for maximum volume here. All right. So we're trying to maximize, which means that we're looking for critical values and we're looking for extrema. Now, if you can tell from this graph where the extreme values are, then you're better at this than I am. I mean, maybe along this ridge here, but I can't tell where the highest and lowest points are. I mean, if I had the GeoGebra graph online that I could manipulate by moving stuff around, definitely. But just by looking at that, no way. Now it's up to you, but when you're considering your next step, you may want to perform a little bit of algebra. I'm not saying you have to distribute this whole thing out, but you may want to consider at least distributing the z to one of the two factors. Because if you do that, then you make it product rule with only two factors as opposed to product rule with potentially three factors. Maybe not even product rule at all, but since these two already have two factors in it, you know you're up against product rule in one way or another. All right, so just to consolidate things a little bit, I'm gonna multiply the second factor by z. The first factor by z. It really doesn't matter, but I want to rewrite that fraction as a negative exponent anyway, so I figure I'd just kind of leave that one be a little bit. Ah, Jacob deGrom, nice. Cy Young. You know, when you're a Mets fan, you got to take what you can get. But back-to-back, seventh pitcher in Major League history, or National League history. Max Scherzer, Greg Maddux, Tim Lincecum, Sandy Koufax, Clayton Kershaw, and Randy Johnson were the only ones to ever do it. An elite group. And the Mets still suck. So that just tells you how bad the team is overall. You could have a Rookie of the Year and back-to-back Cy Young Award winner and still not be any good. What can you do? I remember the first year I really started getting into sports, 1986. New York Giants won the Super Bowl. The Mets won the World Series. I was like, this is going to be great. Man, I picked the right teams. Giants, okay. The Mets, no, never again. All right. So, since both factors involve an x and a z, I have to use product rule. So, first times the derivative of the second. Now, the derivative of the second here is really just going to amount to the derivative of 12x to the negative first. So negative 12x to the negative second. Plus the second factor times the derivative of the first. Same deal. The first part of that first factor is the only thing that has an x in it. So I'm just going to be left with a z there. All right. It's ugly, but the act of finding the derivative wasn't bad. Now, that being said, I probably made a mistake, just because every time I say something's not bad, I screw it up. But feeling pretty good about this one. All right. Which is why I'm not looking up right now, because if I look up, then maybe somebody has their hand up telling me that I made a mistake. No, nobody is. Okay, good. All right, because I felt comfortable with that. So now I need to find my first order partial with respect to y. Now, our derivative is made up of x and z, so I know I'm on the hook for setting partial x and partial y equal to one another, so I'm not going to touch this until I have my, my other derivative. So first, oh, y, force of habit. So first times the derivative of the second, which is just a -2, small favors, plus the second times the derivative of the first, a little more, you have an x minus 4z. All right. So in the first case, there's a common factor that could be pulled out. Maybe that'll help, maybe it won't. But I know I could yank a z out of the whole thing. I can only yank a z out of here, I can't yank a z out of there, so I think I'm on the hook for the output here. So it's one of those things where it's like, yeah, unfortunately, you just gotta dive right in and see where it takes you. All right, but I'm gonna go back to using positive exponents as I go through this distributive property. So multiplying, I'm looking at negative 12z over x. Keep the base out of the exponents, but move it to the bottom. Plus 24z squared over x squared. The other part's easy, so plus 12z over x. Like, all right, we're on to something here. Minus 2z squared. All right, so nice little development. One of the beefier parts of this will cancel out, so we'll take that as a win. It's still a function of two variables, so you know there's really only so much you can do, but you could actually get a solution for this, but I'm going to hold off on that for a minute because you have a common z squared that can be factored out. All right, so but for now I'm just going to write it as 24z squared over x squared minus 2z squared. All right, we'll come back to that in a minute. All right, for the other one, distributive properties, it's a little bit easier because you don't have to worry so much about the negative exponents. So negative 2xz plus 4z squared. All right, but then for the second part, yeah, the calculations won't be that bad, but you do have to distribute. You have to use the double distributive technique or FOIL. All right, so plus, multiply the first terms, it's just a 12. Outer is going to be negative 48z over x. Inner, negative 2xz plus 8z squared. All right, so we can combine a couple of like terms, but that's really about it. So we have negative 4xz plus 12z squared plus 12 minus 48z over x. All right. So, big question is now what? Well, we got to set each of these equal to 0 and therefore equal to one another. But, like I said, we can get away with just setting this one equal to 0 and things will work out. But, if we set them equal to each other, we might get a unique solution. All right, so we're gonna find f sub x equal to 0, f sub z equal to 0, and then equal to each other. All right, so one at a time. 24z squared over x squared minus 2z squared set equal to 0. Add the 2z squared to both sides. We have a common z squared, which makes it irrelevant, so we could cancel it. Now, technically, we really shouldn't cancel it because it would lead to a factor that could necessarily give us a solution, but it should come out in the wash elsewhere. So that's how we're going to handle it. So we'll have 2x squared equals 24. And so divide both sides by 2, you get x squared equals 12. And so x would be equal to the square root of 12. Now, technically, it could be equal to positive or negative 12, but we defined x as a length of the side, right? So we don't want it to be negative. Right? So I'm going to take my other partial and set that equal to 0 and just kind of hope for the same thing to happen. All right, and if it doesn't happen, then try something else. But the something else is not going to be anything crazy, so. All right, so here I might consider running through with an x. Just multiply everything by x. If I do that though, things start getting a little too crazy. You know, you're gonna have an additional x in every single term except for the last one. So you might say, well, I don't see the benefit in doing that. We could try to solve for x, same deal. Like you have x in a couple of different places. So what would be the benefit of that, all right? So you know, the common reoccurring theme might be, well, what would be the benefit of doing that? So you think, I'll try this, what would be the benefit? All right. So the other possibility would be to say, well, I just figured out a value of x. Couldn't I just replace the x's here, because they're supposed to be equal, these two equations. So I could replace the x's with radical 12s. All right, now in our next step or two might amount to the same stuff that you would consider doing, and I'm going to move this out of the way. If you had worked with the x's, but at least we'll get a solution here. You know, that's the thing, that's the idea. So you look at this and you say, well, yeah, we'll get a solution, but it's going to take us the rest of our natural lives to get it. I say, no, it won't, because I'm looking at a quadratic. I mean, it's an ugly quadratic, but it's still a quadratic, right? Your calculator can handle a quadratic, right? So you just use the quadratic formula. Now, maybe you don't want to use the quadratic formula. Maybe you want to use a different technique. That different technique could be using the solver. It could be using a graph. There's a lot of different ways to handle this. If you want the path of least resistance, I recommend just using a graph, and I'll show you that right now. Very mess here, but it's better than the alternative. Everywhere I have a Z, I'm going to put an X. So I can put that function in there. Well, I'll show you the graph and calculator. I'll also show you the solver, right? Assuming that the solver on this one works the same way as the solver on the other ones. All right. I don't like using the zero function on the calculator. I like the intersection function. So what I do is anytime I'm solving a function-based equation, I'll put the left side in as one equation and the right-hand side in as the other, just looking for the intersection between the two. All right, so I would hit graph. Zoom 6 ought to do it because, like I said, it's a parabola. It's an ugly one, but it's still a parabola. So you should get two distinct x-intercepts on your display if you do a Zoom 6. All right. Then do second trace. Oh, well, this one's different. So second trace 5. Yeah, it's different on this one, but second trace 5 is what you're looking for. And then hit, and scroll to the intersection and then hit enter, enter, enter. Let me see if I can figure it out for this. Value, divide, no. Yeah, that's all well and good. Yeah, it's different on this display. Oh, Lord have mercy. This is something. So that's the trace. Yeah, it's given derivatives, antiderivatives. All right, yeah, so on your calculator, second trace 5, scroll to the intersection and hit enter, enter, enter. All right, it'll give you the solution. All right, but let me show you the solver because that's definitely going to work. Definitely, most likely. Although it's a little bit different on your calculators. I might have to slum it and go to the other display just so I could, yeah, I don't think I have a choice. Because I could hand wave my way through this, but then everybody's gonna smile and nod and nobody's gonna have any idea what the hell I'm talking about, so. How's that different from any other class? All right, wise guy. All right, so compute, no, digital link. You just type it in again. So -4, let me just move this up. Okay, that's fine, whatever. -4, and the square root of 12 times x plus 12x squared. 12x squared is what I said. Why are you not listening? Plus 12 minus alpha window fraction 48x over the square root of 12. All right, so hopefully I typed it incorrectly. We'll find out in a minute. Type in the 0. Zoom 6 ought to do it. All right, you should get a parabola, again, because it was an order 2 polynomial. Second trace 5 is intersect. You're just scrolling to the intersection point that you want to find the value of. So I'll get the rightmost one first. Once you get as close as you can to it, hit enter, enter, and then enter again. All right. And it'll tell you the intersection, 1.73-ish. All right, so Z is approximately 1.73. 1.73, I'll say 2.1. find the other one, because it's possible that they both make sense. Maybe you have a couple of different parameters that'll make this box have a maximum volume, but maybe you don't. Maybe it's just the one. So 0.5774 approximately. Yeah, you could. So once you quit out of here, you hit X, brings up the value. You got to do it one at a time though, then math bracket, and see if it converts over. In this case, because I mean, this would be the result of a quadratic formula calculation, so it's going to have a radical in it, so it's going to be pretty nasty.
These ones actually turn out nice. That's rad 3 over 3, and the other one's rad 3.
Right. Okay. Yeah. Now that you say that, that makes perfect sense. Yeah. So. Yeah, because those look like the good old tangents on the unit circle. All right. Now, if you want to use the solver function, so if you suspect that it's going to be a clean radical, square it, and you'll see what it is the square root of. So this is the square that 0.577 and so on. It turned out it was the square root of 1/3, which simplifies down to 1 over rad 3, which rationalizes to radical 3 over 3. So you can get it that way. You could also try the solver. All right, that, depending on your calculator, you might have a different display. So some of the calculators have this display, some of them have other displays. That's why I kind of shy away from this. But if you have, when you hit solver, if you have this display, what you want it to say is y1 minus y2. And so what it'll do is it'll give you a solution in the domain that you state. So if you state y1 minus y2 and then go to x and hit alpha enter, it'll bring you to a solution in that interval. All right. The problem is with the solver technique, it won't give you more than one solution. It'll only give you one solution at a time, depending on the value of x that you have in there as the last stored value. So for example, if I had, let's say, 5 in there as my x value, that takes on the role of the guess when you hit second trace 5. So if I have 5 in there, it's going to drag me to the solution that's nearest to 5. So if I hit alpha enter, it'll bring me to that other solution, 1.732. But if I put negative 5 in here, it'll drag me to the solution closest to that one, which is the 0.5774, right? So you could get it, but the drawback to this approach is you have to know how many solutions there are, and you got to kind of know in what neighborhood they're existing. So it means that you sort of have to have a sense of what the graph looks like. And so if you're already looking at the graph, why not just use the second trace 5 function, you know? So the other calculators, the newer ones, have a better interface, but it still has the same limitations. So that's why I kind of shy away from this. And this technique is really good if you know that there's only one solution. You know, like if you have an exponential function and a line intersecting, they could only intersect at most one time. So you're going to get only the one solution if it exists. But if you have a polynomial function and another polynomial function intersecting, or a trig function, all bets are off. So it's a strategy, it's an approach, but it's not necessarily always going to be the best one. All right. But we have our x's and our z's, so we're in good shape. But what we want to do is also be on the lookout for any other possibilities. So you might consider setting your first order partials equal to one another and solving. But I can tell you that that's not really going to accomplish much of anything, because we've already gotten all the solutions that we're going to get. All right, so for our purposes, it's going to kind of be a waste of time. All right, so we have our critical values. The issue here is that radical 12 corresponds to two possibilities. All right, so my critical values would be radical 12 comma radical 3 over 3, and radical 12 comma, radical 3. They both could serve as points that would lead to maximum volume. Maybe one's a max, one's a min. Maybe neither of them are maximums. This is a trick question. I mean, it's not. But you never know. You know, like it could be one of any of the three possibilities. All right, so what I want to do is look at my second order partial with respect to x. All right, so that's less entertaining than just typing stuff into the calculator, but more manageable because we took the time to simplify. Our first order partials. All right, so my second order partial with respect to x. Right, this thing is dying on me. All right, now I'm going to rewrite it a little bit. 24z squared x to the negative second, minus 2z squared. And the other one, I'm going to write it as basically the same thing, except any fractions I'm going to make into negative exponents. All right, so just got to dive in and do it. Negative 48 z squared x to the negative third f sub yy zz 5%. It is not charging for some reason. All right, so negative 4x plus 24z, and then we'd be looking at minus 48x to the negative first, and then we need second order partial or mixed partials. So this is where you pick and choose your battles, because I'm looking at this one and I'm looking at that one. I want to decide which one's going to be easier. Doing my f sub x in terms of z, or my f sub z in terms of x. All right. It looks like it might seem like it's 6 of one, half does the other, but if I do f sub z in terms of x, then this stuff would wipe out. All right. So that's what I'm going to do. So I'm looking at negative 4x plus 48z to the negative second. All right, so zx, oh yeah, so it's negative 4z. I think I said negative 4x. Gone, and then plus 48zx to the negative second. All right, so discriminant, it's going to be the product of these two things with the substituted values in there. So it's a question of, do I want to substitute them in now or substitute them in later? Honestly, we're at a point now where it doesn't really make that much of a difference. So I know that if I replace my x's with radical 12s, that's going to be fine, because that's going to be consistent throughout the whole process. All right, so I could just chuck that in right away, because I don't have to vary that. When I go to substitute my z values, then I have to do it separately, because I have two different z values at work. All right, so come up with a general statement maybe. and then go from there. All right, so, or we could plug in the 12s, the rad 12, and then go from there. There's a lot of different avenues here. So negative 48 z squared radical 12 to the negative third times negative 4 radical 12 plus 24z minus 48 over the square root of 12. And then the other part is just going to get squared away. So negative 4z plus 48 times 12, because I'm sorry, 48 over 12, because the x to the negative second, we're plugging in a rad 12. So that would be radical 12 to the negative second, so 12 to the negative first power, so 1 over 12, so 4z. So, I mean, it's a little something, but it does cancel away. All right, when you plug in the the x value into my my mixed second order partials. So then it's just a matter of figuring out what this is going to be for our two different z values. All right, so it's just more computation.
When are we gonna have a test on this subject?
What does the calendar say? Like we talk about this or something. December 9th. So negative 48 z squared over the square root of 12 cubed. So it's just a question of how you want to handle that part of it. All right, so the radical 12 raised to the third power, well, it's already to the 1/2 power of the 12. You could simplify it and then cube it out if you want, but just bear in mind, ultimately we're looking for the sign of my discriminant. All right, so you could put in the work, but I don't know how much effort you want to put into simplifying this if we're only looking for the sign of the result. All right, so, well, I guess with that in mind, maybe don't even bother with that. We could just jump right to the substitution. All right, because I'm looking for the discriminant when z is equal to radical 3 over 3. So negative 48 times radical 3 over 3 squared times radical 12 to the negative third power multiplied by negative 4 radical 12 plus 24 times radical 3 over 3 minus 48 over rad 12. All right, so we just have to crunch these numbers, pop it into the calculator, see what it gives us. All right, so that's one computation. The other computation is the same thing, just plugging in a z value of radical 3. So I'll do this and then we'll run them through simultaneously. So plugging in the radical 3 is going to be a little easier because it's just, every time it's squared, it's just going to be 3. So radical 12 to the negative third plus, well, this is still 24 radical 3 minus 48 over radical 12. All right, so we're just looking for the signage. Positive or negative, that's all I care about. Just a fair amount of typing needs to happen. Times, well, that's the same as 1/3. So I can just make that negative 16 times the square root of 12 raised to the negative third times negative 4 square root of 12 plus 8 radical 3 minus 48 divided by the square root of 12. Positive. All right, so we're looking for a max, so that's no help. Oh wait, so that's fine. Sorry, I misspoke. The second order partial with respect to x is going to drive this whole thing in a sec. We don't want negative for a discriminant because that would be saddle point. We don't want 0 because that would be the worst possible thing ever. All right, that would mean that there is not anything conclusive here, which would mean that we wasted every ounce of our time doing this. All right, fortunately, that is not the case, at least for that part. And negative. Okay, so that part, irrelevant. So the radical 3 is out. The radical 3 over 3 is my keeper. All right, my handwriting is going off the rails here. But the radical 3 over 3 is the one that I want as my critical value. Now I just got to make sure that that's going to give me a second order partial with respect to x. That is, I need it to be negative. And it is. Yes. Because no matter what I plug in for z, it's always going to be positive. As long as I plug in a positive number for x, that's going to be positive. So the fact that my leading coefficient here is negative, I can now say that my second order partial with respect to x at radical 12 comma radical 3 over 3 is going to be negative. Therefore, we're looking at a relative max at radical 12 comma radical 3 over 3. All right, now I do have to go back and apparently have to, look at that, jeez. Have some sense of scale for crying out loud. Like telescoping series. So I do have to go back, I'll come back to that in a second, and answer the question. Find the maximum volume that such a box can have. All right, so that max volume is based off of this, all right, which in turn is based off of that. So I have to plug my x and z values into this expression. All right, so that part in and of itself is not going to be bad, because all I'm going to do is replace my x's with radical 12s. And my z's with radical 3 over 3. 12 divided by radical 12 is radical 12. Minus another 2 radical 3 over 3. And then just another radical 3 over 3. All right, so that would be my max volume. We're talking about approximately 3.1 cubic meters. All right, so substitute back into the original function. So f sub xy, replace it with radical 12 comma radical 3 over 3, and you get approximately 3.1 cubic meters.